Tableau 4, a little set theory. In our last module, we discussed chance in commonplace settings. A basic feature that arose repeatedly in these settings was in the consideration of aggregates of outcomes, collections of outcomes, sets of outcomes. The mathematical language of sets provides the alphabet with which we describe elements in the theory of chance. So at this time, it'll be convenient for us to remind ourselves the basic elements of sets and operations on sets. We will not need very much from the basic theory. This is the kind of material which is traditionally seen sometime in a high school curriculum in mathematics, and we will review the basic elements that are needed for us to describe chance elements in this context. For those of you who are familiar with basic sets and set operations, you could jump ahead to the summary, quickly refresh your memory of the basic concepts, and then move on to our development of the theory of chance. For others, stay with me and we will develop the basic elements. So to begin, what is a set? A set is a collection of objects. To focus our attention, pick something quite commonplace. Let's, for example, pick a collection of fruit, say pears. I happen to like pears. Now, what I've shown you is a collection of 8 different kinds of pears. I understand, actually, from the Pear Growers Association. I didn't know there existed such an entity, but the Pear Growers Association actually claims there are more than 3,000 varieties of pears, but that seemed a bit excessive for today's lecture, so we'll begin with 8 pears. And you notice these pears are distinctive. They've got distinctive features, colors. The key element for us is that they are distinct types of pears. And we represent it mathematically by enclosing the collection in curly brackets. And as always, in this kind of context, when we are dealing with collections of objects, aggregates of objects, we describe it mathematically succinctly by using curly brackets. Okay, so these curly brackets then connote, for our purposes, 8 different kinds of pairs. Now, the semantics here are not particularly relevant for our purposes. It is not so critical that the first pair on that list is an untrue pair, or perhaps, let's say, the 4th or 5th pair on the list is a Bosc pair. What matters is that there are 8 different objects. Now, we could have described these objects quite differently. Instead of just putting them in a basket and saying, well, here are 8 fruit types, we could have listed them, say, by their names. For example, Anjou, Bartlett, Stark Crimson, Bosc, and so forth. What is material here is that these names, these images, represent objects which we have a common understanding for. The individual pairs have particular characteristics, shape, color, perhaps taste, texture, where they are used. These provide the underlying semantics where we want to use these collections. And this semantics is ordinarily not particularly relevant for our purposes. What matters is there are 8 kinds of objects. Now, with this kind of understanding in mind, we could give these objects any kind of name we wished. For instance, we could simply call the objects 1, 2, 3, 4, 5, 6, 7, and 8. Implicit in this kind of description is a compact, a common understanding, a dictionary of translation that one assumes has been established ahead of time. So in our case, 1 could represent the first kind of pair on that list, perhaps an Anjou. 2 could represent a Bartlett, the second pair on the list, and so forth. With this common understanding, we might just as well deal with a collection of 8 numbers, 1 through 8. Or, if you wished, letters A, B, C, D, E, F, G, and H. The selection of description is dictated by common necessity, and an overriding idea is the simpler the better. Nothing is wise that complicates existence, and in this case we pick simple names, simple descriptions for objects, as long, of course, as there is no possibility for confusion. What about other objects that might arise? Well, let me think about another, again, visual kind of setting. You're all familiar with the idea of graphs in the calculus. We describe functions typically visually by drawing a graph of that function. Graphs appear in other areas in mathematics as well, and in graph theory, graphs connote entities which are described by two kinds of objects, commonly called vertices and edges. You could think of vertices as dots on a page, one dot per vertex. And you can think of edges as connections between the dots. Draw lines between the dots to create edges. Now, here's a very simple kind of graphical structure. Think of a graph on three vertices with some description of edges. Okay, and here we go. Three vertices, I've numbered them 1, 2, and 3. They appear as red dots on your screen. And now the graph is completely described, once I tell you there are three vertices, by which edges, which lines are present. So we can now, in a very lexicographic way, describe the various possibilities for these entities, graphs on three vertices, by describing systematically graphs with no edges, graphs with precisely one edge, graphs with two edges, and finally graphs with three edges. You should convince yourself that I have listed all possibilities here. There are 8 different possibilities for graphs on three vertices. Now, where do these kinds of things arise? Well, they arise in all kinds of settings in the 21st century. If one thinks of a very complex social network like Facebook or like Twitter, we can imagine the participants as vertices in a very large graph. And connections between vertices, for example, are friends in Facebook, people who see each other. Now you understand, or you begin to get a feeling for why objects like these could become important in a variety of engineering, scientific, and mathematical settings. Once we have established that we are going to be dealing with graphs on three vertices, then we could have an implicit dictionary of translation, and without explicitly drawing them or exhibiting them or giving you graphs in a basket, simply give them names. A dictionary of translation might say, let's provide a lexicographic arrangement of these graphs on three vertices, starting with graphs on no vertices, and then building up systematically 1, 2, 3, 4, up to a graph with all edges available on the three vertices, and that's graph number 8. With such a dictionary of translation, the numbers 1 through 8 then completely describe the picture on the left. What about more complex settings? And now, in abstraction, sets, collections that appear routinely, again and again, are collections or sets of numbers. And these have a particular and potent importance. So let's turn to these next. And at this point, we should bear in mind that the kinds of descriptions I've given you of sets is explicit. For example, I've given you a basket, or more formally, 2 curly brackets, which represents this basket, this collection. And inside this basket, I've been putting entities. The entities don't have any particular order. All that matters is what is in the basket, in that collection. And for visual clarity, we've separated the entities by commas. Of course, that wasn't essential if you could clearly separate them. But when we're dealing with an alphabet involving a common theme, sometimes things run into each other, and it'll be useful to visually separate them by commas, spaces, what have you. These are all explicit representations. I've listed everything in the collection. And this makes a good starting point for describing collections of numbers. So let's start with the very simplest collections. The simplest collection of numbers arises in the theory of logic, what is sometimes called Boolean algebra. It crops up routinely in modern-day binary digital communications, where the idea is that the basic element for describing objects is one of two letters, 0 or 1, false or true, yes or no. Now, if you put numbers around these, the simplest description is 0 and 1. In some order, you could say 1, 0 or 0, 1. The arrangement does not make much matter. Again, we enclose this in curly brackets. The context telling us that this is a set, a collection of objects, very simple to be true, on which I'm going to actually build some kind of theory, some kind of analysis. This is an explicit representation of the object at hand. Let's go on to something a little bit deeper. Consider the throw of a die. If we imagine that the die faces have numbers 1 through 6 painted on them, representing the actual pips we see, 1 pip, 2 pips, all the way up to 6 pips. Here's our dictionary of translation. Then it is natural to denote the possible outcomes of the throw of a die by one of the numbers from 1 through 6. And again, we have an explicit representation. But there's another possibility. We could describe this collection implicitly. Okay? And this is going to become important when sets get richer and richer, and it becomes impossible to explicitly list all the possibilities. What would an implicit representation of this throw of a die mean? Well, let's generalize this a little bit. Imagine one had a die with many faces, not necessarily 6. Well, how many faces? Well, I don't want to put an a priori restriction on how many faces the die could have or how many outcomes you could see. So what should I call it? Well, inevitably, I want to call this an algebraic variable, fixed but arbitrary. And again, inevitably, long tradition and custom has inured us to calling such variables n. Why n? Well, because it is inconceivable that I call it anything else. And so now we have a collection of n numbers representing, for example, n faces on a die, n distinct objects, n pairs, n graphs. Again, we enclose it in curly brackets. Now, an implicit representation for this is we now have a dictionary of translation. We've got numbers 1 through n. These are integer numbers. So an implicit representation would be to write down a generic letter representing an element of that set, of that collection. In this case, again, long custom tells us to write down a letter, lowercase n, to represent a typical number. Notice how we've described this. We first write down a generic, a typical element of that set, n, fixed but arbitrary. Put in a colon and say, following this, this object is described by this condition. Now this gives us a generic way of describing more and more complex sets. This is a descriptive or implicit way of describing the set. Let's move on to a slightly richer collection. And where do we go beyond a finite collection? Well, of course, an infinite collection. And the simplest infinite collection is that of the natural numbers. How do we describe them? Well, if we want to try to describe it explicitly, I will start by writing down the number 1, then the number 2, possibly the number 3, and then I realize, well, I really cannot write down all possible natural numbers. There's an infinite number of them, and so we put down a sequence of dots, and the dots means and so on and so forth. This is the idea. This is an attempt at an explicit representation for these numbers. How would an implicit representation look like? How would a descriptive representation look like? Well, we write down a generic letter n and say that this n satisfies the following property. We describe the property that a typical member of the set satisfies. In this case, n is any natural number. And now we have an implicit or descriptive notation for this. Now, this set is widely seen, and it's hugely important, and therefore long tradition has given us a name for it. And this name is a short form which captures the entire set, much like somebody's name is a short way of describing that person. In this case, the name for a natural number is given by a bold-faced letter N. Now, this blackboard bold font means from now on the system of natural numbers, and this is the notation we adopt for it. Where do we go from the natural numbers? Well, history tells us that a zero was discovered somewhere in the Middle East or perhaps India, and once a zero was discovered, negative numbers were discovered, and these then create the family or the set of integers. These are important. We'll see them repeatedly. They have a name denoted by blackboard bold Z, and they connote explicitly all the integers we are familiar with: 0, 1 and minus 1, 2 and minus 2, 3 and minus 3, and so on. And the descriptive notation says this is a collection of letters n, where n is any integer. Still more complex orders of infinity are available, and of course the most common one for us is the real line. The real line now moves from counting objects onto a continuum of objects. The notation or the language for it is blackboard bold R. We denote it by a line, and we implicitly think of a real line of length. We sometimes represent it by an open interval, familiar from calculus, running from minus infinity on one hand to plus infinity on the other. And we describe it by saying it's a collection of objects x. Why x? Again, because it is inconceivable I call a real number anything else, isn't it? And x must satisfy the following properties. It is a real number in the range from minus infinity to plus infinity. Of course, the names we give these objects don't make much matter. We could choose other names for integers. For example, tradition compels us to use letters in the middle portion of the Latin alphabet: I, J, K, L, M, and N, typically to denote integers, N denoting a generic such integer. Similarly, for real numbers, tradition compels us to use letters at the end of the Latin alphabet: S, T, U, V, W, X, Y, and Z, and we use X as a typical or generic member. Now, these kinds of sets or systems are going to be important to us, but even more complex collections can be envisaged.